Hello, we are from Group 5 and we will discuss about corrosions of metals. Metal is strong, but it has a weakness, which is corrosions. It's what happens when metal slowly gets damaged, like when rust forms on iron. But why does this happen? In this video, we will talk about definitions, factors affecting corrosions, example of corrosions, type of corrosions, corrosion testing, prevention methods, and last but not least, corrosions in space.
Electrochemical takes place under two circumstances. When a metal is contact with conducting medium, or metal completely or partially immersed in the corroding solution. The first step involves the loss of electron by the metal due to the dissolution in the corroding medium. If the metal is exposed to acidic environment and metal is above the hydrogen in electrochemical series, develop large anodic area and small cathodic area. So, liberated electrons are consumed by hydrogen ions in the cathodic reaction and hydrogen gas is evolved. If the corroding environment is either neutral or slightly alkaline, then there will be development of large cathodic area and small anodic area. The liberated electrons of anodic reaction are quenched by the reaction with oxygen and water to form hydroxide ions. So, hydroxide ions react with ferrous ions to form ferrous hydroxide, which will be deposited on the surface of the metal.
Okay, 4 factors. Firstly, corrosion rates typically rise with the increased addition of impurities, as these impurities create small electrochemical cells where the anodic part undergoes corrosion. For instance, zinc with impurities such as iron or lead experience a faster rate of corrosion. Secondly, relative humidity affects the rate of corrosion. The rate increases sharply above a specific level called critical humidity. Beyond this threshold, corrosion happens much faster. The heightened corrosion with increased humidity is attributed to the oxide film's tendency to absorb moisture, leading to additional electrochemical corrosion. Then, water acts as an electrolyte, facilitating electrochemical reactions leading to corrosion. Third, the pH level significantly affects the corrosion rate. Lower pH values, acidic environments, mean pH below than 7 lead to higher corrosion rates and more corrosive than neutral or alkaline environments. Then, noble metals like gold and platinum have very low corrosion rates, which are largely unaffected by pH and rarely used for common purpose due to their high cost. Then, metals like aluminium, zinc, and lead experience higher corrosion rates in both acidic and alkaline environments compared to neutral ones. This is due to the solubility of their oxides in acidic and alkaline conditions. And the last one, the presence of oxygen accelerates corrosion. Increase in oxygen concentration usually gives an increase in corrosion rate. Corrosion occurs through an electrochemical mechanism where oxygen acts as the electron acceptor, cathodic reaction. In the presence of water, dissolved oxygen reacts with electrons from the anodic oxidation of iron.
Next, let's explore an example of corrosions. The first one is Bhopal, India incident. In December 1984, a massive industrial disaster occurred, killing nearly 8,000 people. Toxic gases, including methyl isocyanate, leaked from pesticide plant due to corrosions. This incident happened due to water accidentally entering a tank holding over 40 tons of methyl isocyanate, causing a chemical reaction. This reaction increased pressure and heat worsened by chloroform and iron from the corroded tank. The safety valve opened, then releasing a toxic gas cloud. Next is green patina. Copper roofs develop a green patina due to a natural chemical process called oxidation. This process occurs when copper is exposed to air and moisture, causing it to react with carbon dioxide and oxygen in the air. First, copper reacts with oxygen in the air, form copper oxide. After that, copper oxide will react with carbon dioxide and water in the air to form copper carbonate, also known as a patina. Patina is a layer that protects the copper from further corrosions and gives it its characteristic green color. Last but not least, rust on a bridge. This is happen due to iron is first oxidized to ions by oxygen. In the second step, the iron two ions are further oxidized and combined with water and oxygen gas to produce a hydrated form of iron trioxide known as a rust.
Next, I'll be explaining 4 common types of corrosion: general corrosion, stress corrosion cracking, erosion, and waterline corrosion. Each type occurs under different conditions and affects materials in unique way. Let's begin with general corrosion. First, we have general corrosion, also known as uniform corrosion. This type spreads evenly across the surface of a metal, leading to a rust-like appearance. Oxygen plays a key role in this process, as moisture and oxygen react with the metal. Materials like cast iron and steel are especially prone to this type of corrosion. A good example is when outdoor metal surfaces, like fences, rust over time due to prolonged exposure to rain and air. Next, we have stress corrosion cracking, or SCC. This type occurs when stress on a material combined with a corrosive environment leads to cracks forming. SCC is more common in alloys and happens at high temperatures. For SCC to occur, 3 factors are necessary. First, a susceptible material, a corrosive environment, and tensile stresses, meaning the material is stretched. A practical example could be cracks in pipelines due to both internal pressure and the corrosive substances flowing through them. Moving on to erosion. Erosion happens when metals corrode due to moving fluids, especially when the fluids contain solid particles. There are 2 types of particles in the fluid. First, hard particles, which cause corrosion combined with abrasion. And second, soft particles, which lead to corrosion combined with attrition. Factors like the flow rate of the fluid and any cracking in the material can worsen erosion. For instance, a metal propeller in seawater experiences this type of corrosion due to the water movement and the presence of sand or other particles. Finally, we have waterline corrosion, which occurs in metal tanks that are partially filled with water. This happens because the area below the water surface has low oxygen, making it act as the anode and corrode. Meanwhile, the area above the water, which is exposed to air, has high oxygen and remains unaffected. To reduce this type of corrosion, we can apply anti-fouling paints to the metal surfaces. A common example of this type of corrosion can be seen in storage tanks or ship hulls exposed to both air and water.
Next, we will move to another sub-ideas about metal corrosion, which is corrosion testing. Corrosion testings enable scientists or engineers to evaluate how materials respond to corrosive environments, which involves control experiments. In these sub-ideas, we will discuss about several types of corrosion testing methods, which are commonly used across various industries. The first one is salt spray testing, which is one of the most prevalent and well-established methods for evaluating corrosion resistance. It aims to simulate marine environments by exposing materials to a fine mist of salt water. By conducting salt spray testing, it will provide us with valuable information on the material's ability to withstand corrosive environments. The second one is electrochemical testing methods. These methods are widely used for studying the corrosion behavior of materials. There are 2 common electrochemical methods for corrosion testing, which are potential dynamic polarization and electrochemical impedance spectroscopy, EIS. The potential dynamic polarization aims to measure the corrosion rate by analyzing current potential relationships, while electrochemical impedance spectroscopy, EIS, uses AC signals to study corrosion mechanisms and coating performance. EIS is particularly useful for studying the long-term behavior of materials in corrosive environments. And the last one, we will talk about immersion testing, which involves submerging material samples in corrosive liquids for extended periods. This method allows for the assessment of a material's susceptibility to corrosion or degradation over time under specific conditions. These tests can be conducted in various corrosive solutions including saltwater, acidic or alkaline solutions, or chemicals relevant to the intended application. Okay, so for better understanding, let's take a look on how such spray testing is being conducted in the laboratory by using spray salt chamber. But before that, we need to know why corrosion testing is very important. Okay, so the answer is corrosion testing plays a critical role in managing and mitigating the damaging effects of corrosion, enabling industries to make informed decisions and take proactive measures to protect their infrastructure and equipment.
Now, what are the ways to prevent the corrosion of metals? One of the effective methods to prevent corrosion is catalytic protection, specifically sacrificial anode catalytic protection. This is an electrochemical technique used to maintain a metal surface in a fully or partially catalytic state when it's exposed to an electrolyte such as water or soil. In this system, the sacrificial anode, made of a more active metal like zinc or magnesium, is connected to the metal we want to protect, called the cathode. Both are placed in an electrolyte such as water or soil. The sacrificial anode corrodes instead of the protected metal because it has more negative electrochemical potential. Essentially, the anode gives up its electrons, preventing the cathode from losing its own and stopping corrosion on the protected metal. Over time, the anode gets consumed and must be replaced, but this process ensures the cathode stays intact. This method is widely used to protect things like ship hulls, pipelines, and storage tanks. Let's move on to the second prevention method, self-healing coatings. This technology was developed to address the limitations of traditional coatings by enabling them to repair internal damage automatically. These coatings use healing agents such as monomers, catalysts, or hardeners, which are stored in tiny containers like microcapsules, hollow fibers, or microvascular networks embedded in a polymer matrix. When a crack forms in the coating, the healing agent is released due to stimulation such as physical damage or changes in pH. The release agent fills the crack and solidifies, restoring the coating and preventing further corrosion. This process, illustrated on the left, starts with crack formation, the release of the healing agent, and ends with the crack being fully filled. Self-healing coatings are commonly used in bridges, pipelines, ships, and even in the aerospace industry, where durability and reliability are crucial. This innovative method significantly extends the lifespan of structures and reduces maintenance costs. Now, let's move to our seventh topic, corrosion in space. You might be wondering, can metal corrode or rust in space? The answer lies in the unique environment of outer space. Unlike on Earth, where corrosion primarily happens due to water and oxygen, space corrosion is influenced by factors like vacuum, bombardment by ultraviolet and X-rays, and energetic particles from solar wind, including electrons and protons. One significant factor is atomic oxygen, found in the upper reaches of Earth's atmosphere between 322 to 805 kilometers. Atomic oxygen is highly reactive and can cause significant erosion to the spacecraft materials. This is why engineers have to carefully design materials and coatings for space missions. For protection, we use special coatings like gold, anodized aluminum, and ceramics, which are resistant to atomic oxygen. Additionally, Materials like titanium and stainless steel are preferred for their natural resistance to corrosion. Hence, that's all from us. Thank you.